Now I want to talk about something called weak localization. And once we have done this, we are also going to talk about strong localization. So previously we have seen that quantum corrections are proportional to echo current, which is going to be proportional to 1 over t to the d. And if you integrate this over all times, it's going to blow up in 1 and 2 dimensions, whereas it's going to be finite in 3 dimensions. So we have to use diffusion and return probability to write a correction to conductivity. And let's think about I will use dimensional analysis to get to that equation. But for that, let's consider conductance which I'll use G to note versus conductivity sigma. And I think everybody knows conductance G is equal to conductivity times area divided by length. But this is in 2 dimension. In general dimension, in D1, 2, or 3, we can write this as like this is L squared. This is so the area is L to the D minus 1 in, right? In 3 dimension it's L squared, in 2 dimension it's L, and so on. Then this is going to be sigma times L to the D minus 2, and D is equal to, in our case, 1, 2, or 3. Right, we need to have this in mind, but also previously Landauer formalism gave G was proportional to E squared over H. Maybe I can just write H. Yeah, exactly. And in this case, I need to get something like this. Sigma, I think is proportional to G times L to the 2 minus D. I just take this to this side and write sigma in terms of G. And this is going to be, in terms of dimensions, E squared over H times L to the 2 minus D. Okay, so this is just dimensions. And I also need to use diffusion, and diffusion is P r comma T is equal to 1 over 4 pi dt with D e to the minus r squared for dt. And this immediately tells me, right, the dimension of diffusion constant. So this, let me use L squared is equal to, let me say it in terms of dimension, it's like D times T. Then T is dimension of L squared over D. And we know the correction should be proportional to return probability. So correction should be related to return. And return is, let me write it like return. So dt p of 0t. And if you remember what we did last time, we need to put like a lower cutoff because diffusion starts at least after the scattering time, but it can go all the way to infinity. And this is equal to, from some t0 to infinity, dt 1 over 4 pi d to the d 1 over root d to d. And in terms of dimensions, so I have like, so this is the dimension of this thing is, I have t here, right? This is t, and there is like 1 minus d over 2 here. This one is, and here I have diffusion unit of diffusion constant d over 2. And I just look at here. Did I get 1 minus d over 2? And yes, this seems to be correct. So you can see I need to get something of the L to the 2 minus d. If I can something like this from the diffusion, I can multiply it with E squared over H and I can get the conductivity. But from here I know this thing is T is L to the D over D. So if I multiply this thing with D, D here, D here, D here, the unit of this thing is D times T to the power 2 minus, is it true? This is, no, I think it is 1 minus d over 2, right? Is that correct? Yes. And if I look at this, and dt is, oh yes, so d times t is length, and this thing is length 2 minus d, right? And length 2 minus d is exactly what I need. So this is what I need. Then this thing multiplied with E squared over H is the correction in terms of units. Okay. So delta sigma, first it is going to be negative because we know conductivity should decrease. We are localizing the things. And E squared over H is what we started, and L to the minus 1 is going to be d times some t naught to infinity dt p0 of t. So we obtain this purely from like dimensional analysis, but if you do like some a little bit heavier calculations, something called Kubo formula and all these like advanced techniques, the only difference is like there will be like a factor of 4 here, right? It's not bad. And the factor of 2, 3, 4, 5, 10 is not important. Then delta sigma, I think we have taken this integral previously, minus E squared over H times, let me forget this 4 sometimes, I can put it back if I need to make some equation a little prettier. It's going to be root t, right? This thing is 1 over root t to the power d, and this is in 1d, this is some t naught to like. In 2d, this is log, let me use ln of t naught to infinity, and in, so this is 2d, and this is, if you want, 1 over t naught to infinity, so this is finite. So this blows up, and this blows up. So in 1D and 2D, the correction is going to blow up, and the interpretation is like divergence of delta sigma implies complete localization. Of all states, and this only happens in 1D and 2D. And of course, so what we are saying is like delta sigma is going to blow up, it's going to diverge, but before divergence takes place, we have to like put another cutoff, right? Nothing goes to infinity in physics, right? Upper cutoff should also be terminated with something reasonable before something diverges. So for that, I am going to put some like escape time, and it is again from diffusion. This is sometimes called tau-less time, but from dimensional grounds we can put like an upper cutoff like this. And what we are imagining is like there is like a box of disordered sample of size L, and we embed this inside like a disorder-free region. And once the electrons reach the boundary of the box, there is no more diffusion, right? So that's the upper cutoff. Then this delta sigma is going to be minus E squared over H. Let me also put that for B, and it is going from this T naught to T escape dt. And also let's focus on 2D for the moment. I'll do 1D separately. And it is 1 over 4 pi dt. And if we take this integral, this is going to be minus E squared over H 1 over 4 pi. I think let me cancel these. Also cancel that. So that 1 over pi. I think I have missed factor here. So this is ln T escape divided by T naught. And for T naught, I'm going to let T naught go to scattering time. So let's do that. Tau. And in the like the random walk derivation of D gave us in 2D, it's going to be 1/2 V Fermi squared tau. Then D tau is going to be 1/2 V Fermi squared tau squared, but V Fermi times tau is L squared, so this is going to be 1/2 L squared. Then tau is going to be 1/2 L squared over D. Then I will put this in the calculation. Delta sigma is minus E squared over H 1 over pi ln. So T escape is D over L squared, and tau is the other way, L squared over D. Sorry. So this is L squared over D. Tau is, let's forget these factors, they are not important. L squared over D. Cancel this D with that. And what we find here is minus E squared over H 2 over pi ln L over L. Did I get that right? Yes.
Have you found T escape in the same way that you express tau?
Yes, yes. So in the case of tau, I am using mean free path, right? I need to use a length. In the case of tau, it is like related to mean free path. Escape is related to reaching the boundary of sample, so I use the sample size there. But in a little bit, we are actually going to use something called coherence length, because beyond coherence length, it actually doesn't matter, so you don't have to go to sample boundary. So now let's use the root result for sigma, and it is going to be n E squared tau over m, and n in 2D is going to be spin times d squared k over 2 pi squared, right? And right, this integral goes from 0 to k Fermi, and if you take this integral, okay, let me assign this like a homework. It's like a trivial thing you probably did in 409, and it's going to give you k Fermi squared over 2 pi. Then I plug this in here, so this is E squared tau over m, and this is K Fermi squared over 2 pi. So this is the density. And what I want to do is, so here K Fermi times tau is equal to m V Fermi, this is P divided by h bar times tau, and m V Fermi times tau is L, so this is going to be m mean free path divided by h bar. And I put this back here, so this is E squared over m, so this is K Fermi over 2 pi. There is like 1 K Fermi and 1 tau, and for that I'm going to write it like m L over h bar. So m's cancel, and so this 2 pi is going to cancel the bar of h, and this is going to be E squared over h K Fermi times L, right? So we obtain exactly what we want, E squared over h times K Fermi times L, and this is the correct dimension in 2D, so this is 2D. Then when sigma minus delta sigma is equal to 0, this is full localization, and this one will give us E squared over h K Fermi times L. So this is this result, and for the correction we calculated this result. Let me just copy this. So these are, they are equal, and that means L over L. So this this quantity, okay, cancel this, is going to be e to the pi. I am taking pi over 2 here, pi over 2 K Fermi times L. Did I get it right? Yes.
Is there a problem with signs here? I mean, we took delta sigma as negative, but then...
Yeah, this delta, I think yeah.
It should be plus.
This one should be plus, but you should have to remember this is minus, yes. Yeah, sorry about that. A little bit messy here, but you are absolutely right. So, and this is the correct form. So what this says is like, okay, so this is the scale L where quantum corrections are important, right? If you are below this scale, you don't have to worry about quantum corrections. But what does it tell us? So the scale is L is proportional to some L times e to the pi over 2 K Fermi L, but the beginning of this calculation was K Fermi times L is much bigger than 1. So this is an exponentially large quantity, right? So you have to go to an exponentially large scale to see the quantum corrections. And quantum corrections are there, but the problem is if you tell an experimentalist, can he or she see it? And this calculation tells us, no, it is very difficult because you need to go to very large sizes. So that's exactly why we call it weak localization. And this is only weak in 2D.
Experimentalists sometimes talk about some trapped states. I mean, are they related to these fully localization?
Trap states? I mean, like our argument is like, so there's like a full spectrum, right? In this spectrum, some states can be localized, some states can be delocalized, and the question is, am I going to have like a system which is insulator or metal, right? Because experimentalists, when they measure, it's either metallic or insulating behavior. And if you are saying that there are like quantum corrections are important, this whole like long elaborate calculation says in 2D everything should be localized, but only in like very large scale. So sometimes we replace this L with coherence length. So the coherence length is like psi is L times e to the pi over L times K Fermi L. And if you go, your sample may be larger than that, but these sample sizes of this coherence length are almost like disconnected conductors, right? So in that sense, it makes more sense to consider a coherence length like this. And let me, speaking about experiments, let me show you the experiments. So we said the key mechanism is interference between two different loops. Like I have like loops, right? And if I transfer the loop clockwise or counterclockwise, it makes all the difference. But suppose I put like a magnetic field, right? And when I put magnetic field, I break time reversal symmetry. And if I break time reversal symmetry, this interference between these two loops is going to be destroyed. Then the idea is like I can probe this effect by just looking at the change of conductance or resistance with magnetic field, and this is exactly the experiment that does that. So what is happening here is like you can see this is like magnetic field is 0, and this is like a low temperature order of 20 Kelvin, right? To see the quantum effects, you need to go to low temperatures. And as you increase magnetic field, resistance is decreasing, right? So this is like negative magnetoresistance. A little bit terminology, but it's okay. And what this means is like as soon as you turn on the magnetic field in positive or negative direction, resistance is decreasing. That means conductance is increasing. And if conductance is increasing, that means localization is being destroyed, right? This effect we are talking about is destroyed with magnetic field, and that's exactly the scenario we have outlined. But what is happening at like very low temperatures and very small magnetic fields is somewhat more complicated, right? There is here a very tiny window of positive magneto resistance. By the way, this is also experimental observation, so I'm not making this up. And this is a little bit more complicated, right? We have to be a little bit patient. I don't know if we have, so this is 14th, maybe 1 or 1.5 months. We may get there, but this is related to spin-orbit coupling and something what we call Barry phase. So we may also come to discuss this effect at some point, hopefully. But for the moment, let's not worry about that. For the moment, what we see is exactly the weak localization in the experiment. So I want to repeat this calculation in 1D. So let's calculate. In 1D, if you do exactly the same line of calculation, what you find is like all states are localized strongly. And that's why we call it strong localization. And this is in 1D. So again, what we are doing is like we start with the root formula. So this is n e squared tau over m. And what we did was calculate n, and n in one dimension is like 2, right? And this is dk, and in 1D I need to sum over minus k Fermi to plus k Fermi, like that's the one-dimensional geometry, right? And this is going to give me 4 times k Fermi, simple integral. And if I plug this in, I'm going to find e squared tau over m for k Fermi. And I want to take this tau to here. Let me write it in 2 steps, not to get you lost. So this is k Fermi tau here. And for k Fermi, I'm going to write it like m v Fermi over h bar. V Fermi times tau is L. Cancel these m's. And it's going to be e squared over h bar times 4L. Let me write this, e squared over h bar times 4L. And so this is sigma. Now we need to look at correction. Correction is delta sigma, and it is equal to minus E squared over H. This 4D, and it's going to go from tau to T escape time, and it's going to be dt 1 over 4 pi d 1 over root t, that's in 1D, and this is going to be minus E squared over H. Yeah, there are some factors, you don't need to worry about this. It's like, let me write so there are some numbers, I'm skipping the numbers. It's going to be root t escape minus root tau. And d times t is the length scale, so this is going to be minus E squared over H. So this is L minus L. So I'm doing exactly this. So d t escape is okay, this is L squared, so this is not going to be root L, this is L, and d tau is going to be, there's 1/2, but let's not worry about, there may be factors here, but let's not worry about that. So L squared, so this is also not squared. And we are saying localization happens when sigma, okay, let me write plus sigma plus delta sigma is equal to 0, and this is going to give us, I'm comparing this line with this line, let E squared over H are gone. What I need to compare is, like, at the end I have L minus L, okay, L minus L is equal to something like L, and now we identify L with some coherence length, and what we find is like coherence length of order of L, maybe 2L, but it's okay. So we find something exactly opposite of 2D. In 2D we found this coherence length, or the length at which this correction becomes 0, to be exponentially large. In 1D it is very small, it is order of mean free path, right? So this is order of mean free path. What this means is, like, within doing 1 or 2 collisions, you already get localized, right? All you can do is maybe 1, maybe if you are lucky 2 collisions, and that's already local, and that's already the condition for this to be 0, and that's why we are calling this strong localization. And this happens in 1D.
Can we compare these two models side by side? I mean, in the previous case, in 1D, the conductance was blowing up.
Yes.
So, like infinite conductance.
So what we are saying is, like, we have like some de Rode contribution, and we also have this quantum correction. Mm-hmm. And initially what we said is, like, quantum correction blows up if you take t is equal to infinity, right? So you are taking return probability, and return probability technically from t0 to infinity dt p of 0t. But we say that, like you have some limited time, right? And this limited time is defined either by, like, reaching the sample size, or, like, maybe, like, not even before reaching the sample size, maybe there's like some coherence length. You reach there, and beyond that time is already irrelevant. So I need to put a cutoff here, and we put the cutoff by calling it like some escape time. And in 2D it was logarithmic, right? This integral gave us something logarithmic. That's why this coherence time was exponential, right? This side by side, so this psi was order of e to the pi over 2 k Fermi L. This is in 2D, and that's an exponentially large scale. So that's the scale where you see the localization. That's why we said it is weak. And so this is 2D, and in 1D we are finding psi is order of L. So mean free path, I mean, is, of course the scales are like something like that. So smallest is lambda Fermi is much smaller than L, and we are expecting this to be much smaller than some coherence time, and we expect this to be much smaller than sample size. And if your sample size is like order of coherence time or smaller, you can just delete this and put this like that. But in 2D, we see from this equation, you are not going to have enough size to localize, whereas in 1D, even like if you have like a very tiny sample, it's going to be localized. So that's the argument. And okay, you may or may not have time to do this. So there's like something called transfer matrix method in 1D, right? We wrote the Anderson model and we diagonalized and we showed how localization plays out there. But there's actually an analytical way to do that, and it's called transfer matrix method. I didn't show this, but I think you can look at this. We may or may not talk about this at some point. If you do that, what you find for conductance is like something like that: 2e squared over h, e to the minus L over xi. So this is the sample size, this is the coherence time, and what this says is, so if L is much bigger than xi, this goes to 0, like complete localization in the case of a very large sample. And in the case of like very small sample, if L is very small, this is going to go like L over xi, right? I expand this, and this maps to Landauer formula. I mean, you can search this, but I don't know. If I have time, I may show how to do that calculation at some point. Any questions? So this, we talk about 2D, we talk about 1D, and last thing is, let me also think about 3D. And in 3D, we have like a metal insulator transition. So delta sigma is finite in 3D, and we don't have, that means no localization. And so this, all of these arguments are done for, as you remember, K Fermi L much bigger than 1, or there is like 1 over K Fermi times L, which is like a small parameter. And in that regime, in 3D, you have like metallic behavior, and you can forget about quantum mechanics, right? Like Drew the calculations, almost 100% correct. But if you go beyond this regime by increasing disorder, then at some point you can localize, and then that's what we called metal insulator phase transition. And I think I'm not going to talk too much about this, but like there are just to expose you a couple of things. So typically there are different kind of phase transitions. A phase transition can be like either first order or continuous, and most of the phase transitions we study in physics are continuous phase transitions, or like so-called Landau type phase transitions. And in Landau type phase transitions, there is some coherence length psi that diverges at critical point. And the conjecture is that this metal insulator transition is also like that. It's like a continuous phase transition in which coherence length diverges at the critical point. And if it diverges in the critical point, if you remember, this sigma is equal to E squared over H, L to the 2 minus D, and this is going to map to E squared over H, 1 over something like psi in 2D, in 3D. And if psi diverges, that means at the critical point, sigma is going to be 0, and it's going to increase continuously from 0 to some finite value.
Is this transition second order?
Yes, I mean, in the old language, it is second order, right? But in the modern language, we don't say like first, second, or third order. Yeah, your answer is yes. And this second order, the transition being second order is also like experimentally, it seems like experimentally correct. But there are like some subtleties. There's like electron-electron interaction and things like that. But you can see it Gerwin Yang if you want to know about more about that. I think I'm going to stop here. Any questions or comments?